Hello, Matthews Gatos here. We're going to do Chapter 8, Logarithmic Functions. And in this section, we'll cover 8.1, which is Understanding Logarithms. What are they? When do we use them? What's the graph look like? And how are they related to Chapter 7, Exponential Functions? So let's go back to Chapter 1 and review what an inverse is. An inverse is anytime I have x and y and I interchange them to become y and x. In other words, elements of the domain become elements of the range and vice versa. So algebraically, I can solve for an inverse by switching x and y and solving for y. Now, if the inverse is a function, we use function notation, f inverse of x, or if y is not a function, I just use y inverse. Now, graphically, the inverse of f of x is reflected about the identity line. And the identity line is called that because all the points on here have the same x and y coordinates. So any point on that line will have the same x and y coordinates. For example, I could have -2, 2, or 0, 0, or 0.5 and 0.5. Those would all be on the identity line. So let's look at original function and its inverse. So let's say I'm talking about this exponential function, y equals 2 to the x. I know from chapter 7 that's an exponential function in which the base is 2, so it's an increasing function. So I can just take my values of x, put them into my equation, and figure out what the y values that go with it are. And then using that table of values, I can graph what my function looks like. And it is, in fact, an increasing exponential function. Now let's look at its inverse. I'm going to take all of my x values and make them y values, take all of my y values and also make them x values. So taking that table of values, I can graph it, and this is what the graph would look like. Notice the equation, y equals 2 to the x, has an inverse of interchanging x and y, x equals 2 to the y. And you can also notice about the identity line, they are in fact reflected. So look at this part here where I'm going to be going from positive 1 y-intercept, and I'm going to be kind of curving upwards. The reflection about the line y equal to x starts at an x-intercept of 1, and it's also curving in the opposite way. So you can see that they have been reflected across that line. Same for these pieces here. So let's compare these two functions side by side and look at some of the key points. So the base, you can see the base of both of these is 2. They're both exponential functions, just reflected about that line y equal to x. For the exponential function, my domain is any real number because I can put anything I want in for my exponent. Now for the inverse, the range, because that's the definition of an inverse, the range should also be all real numbers. And you can see graphically that that is true. The range of my original function was everything above a y value of 0. And the reason that is because I have an asymptote at y equal to 0. So if that's the range of my function, it would also be the domain of my inverse. So you can see on your inverse, everything is to the right of 0 for x because there is an asymptote. So those are also switched around as well. Now my original function does not have an x-intercept because there's an asymptote. So my inverse should not have a y-intercept because everything that's true for the domain is now true for the range. In my original function, I have a y-intercept at 1, so I should expect to see an x-intercept at 1 as well. So I want to look at now what happens when I have a base that is in between 0 and 1. Well, all the same properties hold true. So if I have a base of in between 0 and 1, I should expect to see an exponential graph that is decreasing. So looking at my table of values, I'm going to take all my x values and put them in here and figure out what the y values are that go with it. Then together with this table of values, I can graph what my function looks like. So putting it together on the graph, you can see it is a decreasing exponential, still has a y-intercept right at 1. So let's graph the inverse. I'm going to take all of my x values, they are now y values. All of my y values will now become x values. So looking at this table of values, I can now graph the inverse. So putting those together on the graph, it's going to look like this. I have my original function, y equals 1/2 to the x, and my inverse, just switching around x and y, is x equals 1/2 to the y. Now, this one here, it's a little bit harder to see that it has actually been reflected about the identity line, but I want to show you that it has. So let's look at my original function. So it has a y-intercept at 1, so it kind of curves down to the y-intercept. The inverse has a x-intercept of 1, and it also curves downwards. So you can see that this piece here has been reflected about that line, or vice versa. And the same is true for these parts here. You can reflect that across the line y equal to x. So harder to see that reflection, but now that I've drawn it in there, you can see that it is true. So again, we're going to compare these two here side by side. So in this question here, they both have a base of 1/2. So they both have the base of 1/2. It's just the x and y that were changed. The domain of the original, x is an element of the reals, will be the range of the inverse. The range of the original will be the range of the inverse. So everything is lining up like it did before. The original graph, the exponential graph, has an asymptote at y equals 0, the inverse at x equal to 0. The original graph had no x-intercept, the inverse has no y-intercept. The original graph had a y-intercept at 1, so the inverse at 1. So you can see everything in this table is true, even though the base is in between 0 and 1. So I'll let you in on a little secret how I drew these graphs on the calculator, because there is no x equal button. So since there's a no x equal to button on my calculator, only a y equal button on my calculator, I'll show you how I graphed these. So on the calculator, you can always draw the inverse, you just can't come up with the equation yourself. So given a function's equation, the calculator can graph the inverse, and this is exactly what I did. So I put my equation into y1, and then I went out and I drew the inverse. Now the calculator needs to know what you want to draw the inverse of. So this is on my main screen. So after I went into y equals, I went out onto my main screen by just doing second mode to quit and go out to my main screen. Okay, once I did that, I did draw inverse. It's in the draw function, which is right above program, so second program. And then I have to tell the calculator what I want to draw the inverse of. Well, I want to draw the inverse of what I have in y1. And so you can see there is the inverse that it drew. Okay, so it doesn't give you the equation, but it does graph it. Now, this idea of graphing the inverse is a bit of a problem because I don't have a x equal button, so we've overcome that. But I want to look at another way that you could do it if you wanted to enter or figure out what the equation of the inverse is in terms of y. So two different ways of coming up with an exponential function. Okay, so an exponential function for the inverse, we can interchange x and y. So the base stays the same and x and y are interchanged. So this is what we were doing before, writing out the equation. Okay, but the inverse of an exponential function is actually a log function. So I can do the inverse by switching x and y, so switching the domain and the range, or I can do the inverse by doing the inverse operation. So the inverse of exponentiation is logarithmic. So it's like the inverse of adding is subtracting, multiplying is dividing. The inverse of taking an exponent is taking a log. So in that case, I can just do the log. So I can have y equals log base b of x. And I just want to show you on the calculator that that is in fact the equation. So if I go into my calculator, I can actually graph this log to show you that it will give us the same graph as the inverse. So let me just show you, good to see those steps anyway, of what I was doing. So let's put into here, I'm going to put in 2 to the exponent of x. Okay, and then I'm just going to graph it. So there is 2 to the exponent of x, nice increasing graph. So if I want to do the inverse of that, let's go out and I'll show you the steps for that. So we're going to go second program for draw, and here's all the things you can draw. We want to draw an inverse. So we want to draw an inverse of what we have in y1. So to get into y1, I go alpha trace, and then I choose option number 1. So I want to draw the inverse of what's in y1. Okay, so there it is, a little bit slow, but it's chugging along. Here it comes, and there it goes. Okay, so I know that that's the inverse. What I want to show you is this equation right here, for what we know right now, is x equals 2 to the y, but I want to show you that logs are actually the inverse. I'm going to get to how I'm entering in the logs in a little bit later, but for right now I just want to show you that if the base is the same, it's still going to give us the same graph. So what I should expect to see is the exact same graphs I had before, except the red graph will draw on top of that inverse graph. So you can see the bases are the same, it's just log, and log is the inverse operation. So let's hit graph and see if that actually works, and you can see it's drawing right over. Now, with logs, the pixelation on your calculator is, it like to get into here, it has to be really tiny, pixelated, but I assure you that this here, it draws down. It's just you cannot see it. So you can see that those two graphs are the same, which, going back to my notes, tells you that the log is actually the inverse of the exponent. So this is good news to us because we really want to have a y equals equation. We don't want to work with x equals. We want to work with y equals for our functions. So long story short, the base stays the same, and it is the log that makes it the inverse. So let's look at the graphs of log functions, very similar to what we did with exponential functions. Okay, so here's the two different types of log functions. Now the base is the same, so it behaves in the same behavior. So between 0 and 1, I have a decreasing graph. You can see as x gets bigger, y is getting smaller. If the base is greater than 1, I have an increasing graph. As x gets bigger, so does y. Okay, they all have an x-intercept at 1. They have an asymptote at x equal to 0, and they have no y-intercept. So exponential and logarithmic bases behave in the same way. So let's look at numerically what a log is, since it's the inverse of an exponent. The log is the exponent the base needs to be raised to get the argument. So just so that we are okay on our terminology, I want to make sure that you know when I have a log, the little number down here, the subscript, is the base, and the big number up here is called the argument. And to be honest, I have no good argument why it's called argument. Okay, but let's look at evaluating each of these. Okay, if I want to evaluate log, this is set as log base 2 of 8. It's basically saying to you, 2 to what exponent gives me 8? Well, using my powers of 2, I know that 2 cubed is equal to 8. So that means log base 2 of 8 is 3, because logs are inverses of exponents. So the answer is the exponent. Okay, looking at this next one here. Log base 3 of 81 is asking you, 3 to what exponent gives me 81? So looking at my powers of 3, I know that 3 to the exponent of 4 gives me 81. So log base 3 of 81 is 4. Okay, these ones here are a little trickier. Okay, so 1/5, log base 1/5 of to the 125. That's just saying 1/5 to what exponent gives me 125? Well, these kind of look backwards of one another. One's a fraction and then the other one's a whole number. I do know that 5 cubed is the same as 125, but that's not what I have. I don't have a base of 5, I have a base of 1/5. So if you think back to 10C and our laws of exponents, whenever I have a base that is 1 over, I've probably taken the reciprocal of it because it was a negative exponent. So for example, if I have any kind of a base to a negative exponent, I can take the reciprocal of the base and raise it to the positive exponent. Now the reciprocal to that, the opposite of that, can also be true. If I have a fraction base, I can come back to a whole number base by having a negative exponent. So what that means is that 1/5 to the negative 3 would be the same as 125. Because if I take the reciprocal of my base, 1/5, that would be 5, raised to a positive exponent. So anytime I have a fraction base, I can take a negative exponent to make it equal to a whole number. So that means that this log has a value of -3. So I want to try that idea over here. Log base 6 of 1 over 36. That's saying 6 to what exponent is equal to 36? Well, I know that 6 squared is 36, but that's not my answer. My answer is 1 over 36. So since the base is a whole number and the answer is a fraction, I want to take the reciprocal, which makes it negative. So this log has a value of -2. So when the base is a fraction and the argument is a whole number, or vice versa, the log value will always be negative. We're going to come back to that and we're going to try that in some other ones. So we'll try that again. Okay, a couple things I want to note. When we talked about in chapter 7, if we had an invisible exponent, in other words, a base without an exponent, it always had an invisible exponent of 1. Well, logs have something similar. Logs have an invisible base though. So if it's just a log, that's called a common log. It's actually an invisible base of 10. So on your calculator, you actually have a log button, and that log button on your calculator is called a common log, and it really has an invisible base of 10. So let me just show you on your calculator here. This log button right here is log base 10. So obviously you're probably thinking, how am I going to do it if I don't have a base of 10? And I'll show you that later. Okay, so remember the base of an exponential function is the same as the base of a logarithmic function. Those can't be negative, 0, or 1. Okay, let's try some more. Let's try some with those invisible bases. So these are all common logs, which means there's an invisible base of 10 in all of these. We just don't write it that way, okay? So let's look at the first one. Log of 10 is really like saying 10 to what exponent gives me 10? Well, 10 to the exponent of 1 gives you 10, so this log has a value of 1. Okay, log of 1,000, or log base 10 of 1,000, is saying 10 to what exponent gives me 1,000? Well, I would have to multiply 10 by itself 3 times to get 1,000, so this log has a value of 3. Okay, over here, log base 10 of 1 over 100. Okay, so that's like saying 10 to what exponent gives me 1 over 100? Well, you know that 10 squared gives you 100, but again, since the base is a whole number and the answer is a fraction, I'm going to raise it to a negative. So the answer to this would be -2. Okay, and then the last one, log base 1/10 of 10,000 is like saying 1/10 to what exponent gives me 10,000? Well, I know that 10 to the exponent of 4 gives me 10,000, but since my base is a fraction and my answer is a whole number, I need to take the reciprocal of that, so it needs to be a negative. Okay, so again, same note there, when the base is a fraction and the argument is a whole number, or vice versa, the log value will be negative. Okay, let's try some more. So let's say I want to take this log and I want to write it in exponential form. So I want to fit this all together. So to do that, what I'm going to use is the circle of logs. So I want you to imagine drawing a big circle from the base to the answer and from the answer to the argument. A big circle. B to the exponent of y is equal to x. So looking at log base 2 of 16 equals 4, using the circle of logs, I can go base to the answer equals the argument. And I know I've done that right because 2 exponent 4 is 16. And here's what else I know. Logs and exponents are inverses of one another. So see how the base stayed the same? And x and y interchange. So instead of equaling to y, it now equals to x. So those are inverses of one another. So you need to feel very comfortable switching from log form to exponential form and vice versa. We'll look at the other way, going from exponential to log form, a little bit later. Let's just practice this idea here. So again, I have a log, but it has no base. So hopefully you remember from before, that has an invisible base of 10. So I could rewrite it as log base 10 of z equals g. So let's use the circle of logs and write that in exponential form. So it will be 10 to the g equals z. Okay, I want to try this a couple more ways because you'll see where this is going. We're eventually going to solving. So let's say I have something like this. I want to write it in exponential form. This looks different than all the other ones because I have this 5 in front, and that's a bit of a problem. So I need to isolate my log first. So I'm going to divide both sides by 5, that's gone now, and I have log base c of f equals n over 5. And now I can use the circle of logs. So c to the n over 5 equals f. Okay, so now that we've practiced that, let's look at why we're actually doing this. We're doing it to solve something like this. If I want to solve for x algebraically, so I can't put it in my calculator and do y1, y2 intersect. I want to do it algebraically. So I'm going to use the circle of logs because right now logs aren't helping me, so I need to switch over to exponential form. So in doing so, I do circle of logs. So 2 to the 6 equals x. And now this equation is much easier to solve for x. So 2 to the exponent of 6 just means 2 multiplied by itself 6 times, which would be 64. Okay, let's try another one. Okay, so solve for x algebraically. Again, I want to do the circle of logs. So I'm going to have x to the 2 equals 25. So this is a much easier equation to solve. So if I have x squared equals to 25, to solve for x, I would just take the square root of both sides. Remembering when I take the square root of both sides myself, I have to remember they are positive and negative. So that means that x can be positive or negative 5. But x is a base. X is a base. And do you remember what we said about base? The base of a log and the base of an exponent are the same, and they both must be positive. So that means that negative 5 is an extraneous root, and x equals 5 only. So x cannot equal to negative 5 because the base must be positive. Okay, let's try one more. So again, I'm solving now for the base. I'm going to use the circle of logs to help me out. So x to the 3/2 equals 8. So hopefully you guys remember how to do that from 10C. Anytime I have a fraction exponent, I raise it to the reciprocal, and to be fair, I do it to the other side as well. So I'm going to have x, because 3 times 2 is 6 over 6, so everything cancels out. It's just like x to the 1, equals 8 to the 2/3. So what that really means is I'm taking 8 and I'm squaring it, and then I'm taking the cube root. So this is x equals the cube root of 8 squared, which is 64. And when I take the cube root, I get 4. That would be my final answer. Okay, so to summarize, the value of a logarithm is the exponent the base is raised to get the argument. Again, because they're inverses of one another. Logs without a base have an invisible base of 10. And then remember, when the base of a log is a fraction and the argument is a whole number, or vice versa, the value of a log is negative. So when the base, I'm going to add in here, of a log is a fraction and the argument is a whole number, or vice versa, the value of the log is negative. To convert between log form and exponential form, you use the circle of logs. And remember, the base, just like an exponential function and a log function, must be positive, but it can't be 0 or 1. So that is your introductory lesson to logs. And another way of referring to logs are as musical wood. So this really was your introduction to musical wood. Why am I calling logs musical wood? Because they're logarithms. So they have rhythm. Funny? I think so. Maybe you don't, but that's okay. You guys can do practice questions 1 to 4 that I have attached to these, detailed solutions, of course, on D2L. And then after you're done that, you can move on to your textbook questions. So I hope this lesson helped, and look forward to seeing you in section 8.2.